Okay, now we have finished the 1 degree of freedom systems and spent some time on it. Now we will start the 2 degree of freedom systems as an introduction to multiple degree of freedom systems. In these systems, we will have more than 1 degree of freedom in which the system vibrates. We will see that the behavior of such systems is richer than the single degree of freedom systems and closer to the real life applications. First of all, let's remember the degree of freedom concept. It is the number of independent coordinates that are required to describe a system. Until now, we have looked at 1 degree of freedom systems in which there was a single mass or a single torsional spring, torsional inertia and a torsional spring, or a pendulum or something, single pendulum. With all these things, one coordinate was enough to describe the system. Now we will go to something more complicated. For example, a system with two masses or two inertias, or for example, a mass and a pendulum, for example, in which we require two coordinates to describe the motion. For example, for this mass and pendulum, we require the x for the position of the mass and theta for the pendulum. And also, for this beam, for example, that is vibrating, we also require two coordinates, such as x and theta. Or you might use x1 and x2 as coordinates. In any case, the plane vibrations of this beam is a 2 degree of freedom system. In general, we can say that the degree of freedom of a system is basically, it is the number, you take the number of masses and then multiply it with the number of motions of each mass. If a mass has a single motion, then for each mass you have 1 degree of freedom. But if a mass, for example, this mass has two motions, then it has 2 degrees of freedom. As I said, we will be studying 2 degree of freedom first, but most of the results we will obtain will apply to multiple degree of freedom as well. So we will be looking at this problem in which there are two masses. There might be springs, there might be dampers, etc. The important thing is that these equations of motions of these systems, x1 and x2 equations, will be coupled with each other. They are combined with each other. So if we try to solve it, if we formulate the problems first, we are going to get matrix equations describing the motion of the system. And if you solve those matrix equations, you will see that you are going to get not just one natural frequency, but multiple natural frequencies. As a matter of fact, for a 2 degree of freedom system, we are going to get two natural frequencies, okay, in which the system, if excited at those frequencies, is going to get into resonance. Let's try to derive the equation of motion for the most general case. For the masses are connected with springs. There are three springs. There are three dampers connecting masses to the ground and masses to each other. And there are external forces, let's say. We write the Newton's equations of motion for each mass, displacing each mass an amount of x1, and then we write the forces, the direction of the forces. The standard procedure is that for x1 we assume x2 is fixed, and then try to find out what is the direction of the force. And then we assume that x1 is fixed, and we move x2 and try to find the direction of the force again. So we find the spring forces, damping forces, and the external force, from which we set the equation of motion, which is Newton's law equation of motion, F equals summation of forces is equal to mass times acceleration. So when you write all the equations, you get a kind of a complicated equation. But if you collect all the terms together, actually you see a structure here. You have the m1 x1 double dot term, then x1 dot term, then another x1 term, and then the x2 dot term and x2 term, they have negative signs as you see here. For the x1 equation, x2 dot and x2 enter with negative coefficients. On the other hand, for the x2 equation, we have x2 double dot term, x2 dot term, x2 term here. But x1 terms now come with negative coefficients. And on the right-hand side, you have the F1 and F2, external forcing terms, as you see. Now, these equations, you have two differential equations, second-order differential equations, which are coupled, which means that x1 equation contains x2 in it, x2 equation contains x1 in it. So these equations can be expressed in a compact form using matrices. For example, you can define the mass, stiffness, and damping matrices as such. If you do that, and if you define the displacement vector, and if you define the force vector as you see, you get an equation very similar to the 1 degree of freedom system equation, only that the equation contains matrices instead of scalars. For example, the mass matrix contains M1 and M2 in the diagonals. The stiffness matrix contains K1, K2, K3, and negative K2s in the off-diagonal terms. And the damping matrix is structurally similar to the stiffness matrix. The force and the displacement are now vectors. They are vectors in 2 dimensions. Another thing is that the mass, stiffness, and damping matrices are symmetrical. That is, their off-diagonal elements are always the same. Okay, so we get a matrix equation. Now let's try to analyze the simplest case in which we have no damping, that is undamped system, and also vibrations are free. There is no force in it, external force. So the equations which we have written in the previous page reduced to some equation like this. We don't have K3 in the third spring. We have 2 equations that describe a system. These 2 equations are coupled now. We can write them as a matrix equation again. Mx double dot plus Kx equals 0. Very similar to undamped free vibrations of a single degree of freedom system, only in matrix form. So we have 2 coupled second order differential equations with constant coefficients. They are second order and 2 equations, so we need 4 initial conditions to solve for them. And the 4 initial conditions are the position of the first mass, velocity of the first mass, position of the second mass, and the velocity of the second mass. If you know these initial conditions, then you should be able to solve this differential equation. Now, how do we solve it? The way we solve it is as follows. First of all, we have our position vector is x1 and x2, position of the first mass and the second mass. The derivative of the position vector is the velocity vector, which is x1 dot plus x2 dot, and the acceleration vector is similarly x1 double dot and x2 double dot. Mass and stiffness matrices are as usual. They are shown here. So you have mx double dot plus kx equals 0 with the initial conditions, with 4 initial conditions. Some of these might be 0. It doesn't matter if they are still the initial conditions. So how we solve it is on the left-hand side. we assume a solution, a harmonic solution. Well, we don't know whether the solution is harmonic. We assume this. And the u is basically, the vector u is the amplitude of the vector x. So it is x1 and x2. First of all, this u is not zero, definitely, and this omega term is unknown. Let's try to take the derivatives of this equation and substitute in our original equation, which is this one, mx double dot plus kx. So u double dot for x, sorry, x double dot would be minus omega squared u sine omega t again. So what we are going to get is the following: omega minus omega squared m plus k u sine omega t equals 0. In which case u sine omega t better not be 0 because there will be no vibration. In which case you will have omega squared m plus k, which is a matrix, times the u vector is 0. Here we have an equation which has two algebraic equations actually, but it has three unknowns. x1, x2 are unknowns in the u term, and also omega is another unknown. We would like to solve them. Omega, as we will see, is going to have two solutions actually. Now, as we know, let's look at the previous equation, this one. We can take the, as you see in this equation, one possible solution here is that u is equal to 0. But we don't want that solution. That solution is the trivial solution. And actually, if the coefficient matrix, which is omega squared m plus k, is non-singular, okay, which means that its inverse exists, then u has to be 0. But this means that there is no vibration in the system, and we don't want that. We don't want no vibration case because that's the trivial solution case. Therefore, we require that the u should not be 0. And if u should not be 0, then this inverse of this thing should not be existing, which means that the coefficient matrix minus omega squared m plus k should be singular. And singular matrices means that its determinant should be 0. And this condition is actually the condition for the existence of solutions for the natural frequencies of the system. For example, for our case of the second order system, the determinant of omega squared m plus k equals 0 means the determinant of this matrix, as you remember, minus omega squared m plus k is the following matrix. And if you take the determinant and equate it to 0, you get a fourth order equation in terms of omega. Actually, it's fourth order, but it is quadratic in omega squared. So you get mainly two solutions, two actual symmetric solutions for omega 1 squared and omega 2 squared. And the positive solutions of this characteristic equation are termed the natural frequencies of the system. So its 2 degree of freedom system has two natural frequencies.